Ever stop and think about how the incredible amount of power needed for, well, everything actually, gets from a power plant to your home? It's all thanks to this invisible, super elegant system that's been the backbone of our world for over 100 years. Today, we're going to pull back the curtain and uncover its biggest secret, the magic of three-phase power.
You know, when you think about it, from those massive generators across the giant transmission lines you see on the highway, all the way down to the transformer on your street corner, this whole complicated dance of electricity, it all boils down to one fundamental principle. It's the real unsung hero of our modern grid.
So, that's the big question, right? Why three? Why not just one big phase, or two, or maybe four? Well, it turns out that for electricity, 3 is the absolute magic number, and we're about to find out exactly why.
So here's how we're going to break it all down. We'll start with why 3 is better than 1, then we'll see how those perfect electrical waves are actually made. We'll look at the 2 main ways to wire them up, discover the genius behind the rotating magnetic field, and finally, see why it's called the engine of industry.
Okay, first things first. To really get why three-phase power is so great, we have to look at what it's improving on, and that's single-phase power. That's the stuff you get out of your regular wall outlet. And for running our world, it's got some pretty serious drawbacks.
The best way to think about it is like this. Single-phase power is kind of like a one-cylinder engine in a lawnmower. It gives a push, then it coasts, then it pushes again. The power comes in these pulses. But three-phase power, that's like a smooth 3-cylinder engine. Just as one phase starts to dip, the next one is hitting its peak. The result is a perfectly smooth, constant stream of power. And that smoothness, it's a huge deal for motors. They run way better without all that pulsing. But the real game changer is efficiency. With a three-phase system, you can deliver the same amount of power using way less copper wire. We're talking about a massive, massive cost saving when you're building a power grid big enough to cross a whole continent.
And check this out. This graph shows that engine idea perfectly. See the dashed lines? Those are the individual phases, pulsing up and down, up and down. But look at that solid line on top. That's the total power. Because the phases are perfectly timed, they add up to a completely flat, constant delivery of energy. No dips, no pulses, just pure, steady power. It's beautiful, really.
So how in the world do we create these 3 perfectly synchronized waves of power? You'd think it would be super complicated, but it turns out the solution is just beautifully simple, and it all starts with the mechanical design of the generator. And this slide just nails that connection. On the left, you've got the physical layout of the generator, the spinning parts, and on the right, the electrical waves it creates. The real stroke of genius here is how the physical spacing of the parts creates the perfect timing in the electricity. So here's the big idea. Inside a generator, you've got 3 separate sets of coils. They're physically arranged in a circle, and each one is exactly 120 degrees apart from the next. Then you spin a giant magnet in the middle. As that magnet passes each coil, it creates a voltage. And because the coils are 120 degrees apart in space, the voltage peaks they create are, you guessed it, 120 degrees apart in time. It's that simple and that elegant. Okay, so we've got our 3 separate phases of power. Awesome. Now we have to actually wire them together to do something useful. And it turns out there are 2 main ways to do this, each with its own special purpose: the star connection and the delta connection.
But before we dive in, we need to get 2 key terms straight. First is phase voltage. That's the power you get from just one of the 3 wires, measured against a central point. Think of it as the power for a single appliance. Then there's line voltage. That's the bigger voltage you get by measuring between 2 of the phase wires. That's the heavy hitter, the power you need for big machinery.
First up, we have the star connection, sometimes called a Y connection. You can see why. The 3 windings all meet at a central point. This creates a 4th wire, called the neutral. And that neutral wire is incredibly handy. It gives the current a place to go, which is exactly what you need for places like a neighborhood where you have all sorts of different loads running at once. Now here's the really cool part about the star connection. The line voltage is always higher than the phase voltage. It's higher by a factor of the square root of 3, to be exact. This gives you the best of both worlds. The utility can send the higher 400-volt line voltage to power heavy equipment, while tapping into the lower 230-volt phase voltage to safely power your home.
All right, the other method is called the delta connection, because it looks just like the Greek rudder. In this setup, the windings are connected end to end, forming a closed loop, and notice there's no neutral point in the middle. This configuration is built for one thing: high-power industrial work.
In a delta system, the relationship is super simple. The line voltage is the exact same as the phase voltage.
This setup is perfect for big, balanced loads. Think of a massive factory motor, where each of the three phases is doing the exact same amount of work. You don't need a neutral wire to handle any imbalances, because there aren't any.
And now we get to the part where all these ideas, the waves, the timing, the wiring, they all come together to do something that is honestly just incredible. This is the discovery that unlocked the true potential of the whole system.
So, let's rewind for a second. Back at the generator, we made 3 perfect waves of current, right? And each one hits its peak 120 degrees after the last. They are separated in time. Now picture an electric motor. It's built kind of like the generator in reverse. It also has 3 coils of wire, and just like the generator, they're physically arranged in a circle, 120 degrees apart from each other. So they're separated in space.
So what happens when you take those 3 currents that are separated in time and you feed them into those 3 coils that are separated in space? Well, you get a result that, as one of our sources says, really speaks about Tesla's genius. What you get is a rotating magnetic field. Now think about that for a second. Without a single moving part, the electricity itself creates this perfectly smooth, powerful magnetic field that just spins. It's like an invisible force, constantly turning all on its own. It's almost magic.
So, a spinning magnetic field. Why is that such a big deal? Why is this single idea the most important outcome of this entire 3-phase system?
It's because this is the principle that makes the AC induction motor work. That invisible spinning field just grabs a metal rotor and drags it along for the ride, creating a smooth, powerful turning force. It's like having 3 people pushing a merry-go-round, each one pushing in perfect sequence, so it just spins effortlessly. This invention is brutally simple, it's incredibly reliable, and it is the quiet workhorse that powers pretty much everything in our modern world.
When you get right down to it, 3-phase power is just a perfect example of elegant physics working silently in the background to make our entire way of life possible. And it really makes you wonder, what other invisible forces are out there shaping our world in ways we don't even realize?